All moving objects have momentum, but if an object is not moving, its momentum is zero. We calculate momentum by using this equation. Momentum equals the mass multiplied by the velocity. In the SI system, the units for momentum are kilogram meters per second, and in the English system, the units are pound mass feet per second. Let's look at some examples. A car has a mass of 1,000 kilograms and is not moving. What is the momentum of the car? Pause the video and see if you can work this out. Since the car is not moving, its momentum must be zero. Here's another one. A car has a mass of 1,000 kilograms and is moving at 20 meters per second. You may pause the video at this time while you calculate the momentum of the car. In this case, the car is moving, so it must have momentum. Remember, momentum is mass times velocity, and the mass is 1,000 kilograms, and the velocity is 20 meters per second. Therefore, the momentum is 20,000 kilogram meters per second. In a closed system, that is a system where we assume no other forces are acting upon it, like friction for example, the total momentum before an event is equal to the total momentum after an event. Sounds complicated, but it's really pretty straightforward. We're going to look at two examples and you'll soon get the idea. Here is a van traveling toward a stationary car. Because the van is moving, it has momentum in the forward direction. As we've learned, the momentum of the van is its mass multiplied by its velocity. The stationary car has no momentum as it is not moving. Now the van collides with the car. Both the van and the car move together at a lower velocity than the initial velocity of the van. The total momentum of the van and the car together is now the same as the initial momentum of the van by itself. So as we can see, the total momentum before the collision is the same as the total momentum after the collision. In other words, momentum has been conserved. Here's another example. This shows a cannon containing a cannonball. Before the cannon fires, both the cannon and the cannonball are not moving, so the total momentum before firing equals 0. When the cannon fires, the cannonball is moving at a very large velocity, so the cannonball has momentum in the forward direction. At the same time the cannon recoils, in other words, it moves backwards. This means the cannon has momentum acting in the backwards or negative direction. The backwards momentum of the cannon equals the forward momentum of the cannonball. So this means the total momentum after firing is 0. So as you can see, momentum before firing is 0 and momentum after firing is 0. In other words, the momentum has been conserved. This relationship can be shown mathematically by this equation, where m1v1 represents the mass and velocity of the cannon, and m2v2 represents the mass and velocity of the cannonball. Notice that the mass of the cannon does not change, neither does the mass of the cannonball. Notice also that since both v1 and v2 initial are 0, the left side of this equation will be 0, and when you solve for the unknown, usually that will be the recoil velocity of the weapon, or v1 final, this value will be negative. Let's work a problem with real numbers to see how this works out.